Thank you, Dan, for the introduction and the invitation to talk today. Many of you have probably heard a little bit about some of the interesting science coming out of the Gravitational Wave Observatory LIGO. These detections of binary black holes that are emerging, binary neutron stars. And so this picture here is an artist's rendering of two neutron stars that are orbiting each other and inspiraling due to the emission of gravitational radiation, which is what these waves are supposed to represent. And so these two stars are about to merge. And as they get closer and closer together, they exert a strong tidal interaction upon each other. And if we can understand that interaction and measure its effect in the gravitational wave signal, we have an opportunity to learn about the internal properties of these really mysterious objects. They're 1.5, 2 times the mass of our sun, but their radii are only 10 kilometers. So they're extremely dense. They're actually denser than the nucleus of an atom. And we really don't understand how matter behaves at such high density. So, understanding these systems is not only interesting from sort of the astrophysics point of view, but also from just fundamental physics and our understanding of the strong force. So today I'll be talking about work my group and I have been doing, studying tides in sort of these extreme environments where the two objects are so close together that you have to account for nonlinear effects. And so before I sort of get going, I'd like to acknowledge and point out some of my collaborators, particularly the students, the graduate students that worked with me at MIT for their PhD theses and are now at postdocs at these various places. And so, one of the goals, as Dan mentioned in my talk today, is to introduce myself and the work that I do to the graduate students and undergraduates in the audience. If anything that you hear today sounds interesting and maybe something you'd want to work on, please contact me. I'd be very happy to meet with you and tell you more about it and maybe come up with a problem that we can work on together. Okay, so just a quick outline. So I'll start by describing tides and closed binaries and why you would want to account for nonlinear effects. Then I'll talk about oscillations in evolved stars. And these are oscillations excited not because they're in a binary system, but because of internal motions within the star. And here too, I'll show nonlinear effects can be important. And then finally, towards the end of the talk, I'll describe another sort of problem I work on related to binaries, which is a phenomenon known as X-ray bursts, which are thermonuclear explosions on the surfaces of neutron stars. And so if you were in my talk in April, you heard the first two topics, but not the third. Okay, so tides are important in just really a wide variety of binary systems. So, for example, in short period exoplanets, they can impact whether the system forms in the first place and how the system evolves in time and whether those planets survive at all. Tides impact stellar binaries as well. So, for example, two sun-like stars in short period orbits. Often these systems start out in eccentric orbits and over time will circularize due to tides. And in the process, the stars will get spun up. And so stars that are in binaries can have a very different evolution. Both the orbit and the components of the binary can really be impacted by tides. And then finally, tides are important in compact object binaries where we think gravitational wave emission is detectable with telescopes like LIGO and in the future with other missions like the LISA space telescope. In physics, when we want to learn about something, we want to probe it, we will perturb it and see how it responds to that perturbation. And so you can think of tides as a perturbation to the star. And by understanding that perturbation and measuring its effects, we can learn about the internal properties of the star. Things like the equation of state, which, as I mentioned, in neutron stars is something that's pretty uncertain, and that's the case as well in some planets. We can learn about things like the internal structure of the star, its evolutionary state, and also things like the rotation profile of its interior, and potentially even see effects of magnetic fields. So these are all things that are sort of hidden from view when we just see an isolated star, but can potentially probe with tidal effects. So let me sort of begin the discussion of tidal physics with the sort of classical system, the Earth and the Moon. So the Earth spins faster than the Moon orbits, 1 day compared to 28 days. And as a result, the tidal bulge that the Moon raises on the Earth and the Earth's oceans leads the Moon's orbit. You can sort of think of this as, the Earth is spinning and dragging the water with it, and the Moon is kind of pulling it back. And the net effect is that the bulge leads because the Earth spins faster. And so if you now decompose the forces acting on the Moon, there's a component pointing towards the tidal bulge. And so there's R cross F, there's a torque acting on the Moon that leads to an exchange of angular momentum. And so the Earth's spin is slowing down at about 2 milliseconds per century, while the Moon's orbit is moving outwards, gaining angular momentum at something like 4 meters per century. And so we can actually measure that motion. So the Apollo astronauts left mirrors on the Moon, and we can shine lasers at those mirrors and measure how long it takes for the light to return, and measure the distance to the Moon to centimeter accuracy. And so we can, actually see the Moon moving away as a result of tides. And so this 4 meters per century is roughly the rate at which our fingernails grow. And so this guy here is showing us how far the Moon has moved away in the last 10 years. Okay, so another interesting system where tides are important are hot Jupiters. So these are Jupiter mass planets in 2 or 3 day orbits, and we know of about 100 of these systems now. The Nobel Prize in Physics last year, half of it was awarded to 2 astronomers who made the first detection of an extrasolar planet around a sun-like star, and that planet was a hot Jupiter. So these are sort of Nobel Prize-worthy objects. And if you now think about the interaction between the planet and the star, stars spin with periods of about 25 days in the case of our sun, much longer than the orbital period of the planet, of the hot Jupiter. And so the tidal bulge that the planet raises on the star lags the planet's orbit, exactly opposite to the Earth-Moon system. And so the tidal torques are in the opposite direction. So the star is getting spun up, and the planet is losing angular momentum, which means that it's falling into its host star. And one of the questions that's been around since the first hot Jupiter was detected in the early 1990s is, what's the rate at which that's happening? What's the rate at which these planets are falling into their star? What the orbits are decaying? And to answer that question, you need to know the efficiency of tidal dissipation. Essentially, what's the viscosity of the star? And so in a little bit, I'll describe some work that my group has been doing to study exactly that problem. Okay, so just a little bit more about how we go about doing these calculations. I like to think of this as sort of a tidal perturbation theory approach, where you imagine you have a spherical star, and now you put a companion near it, and you get this kind of ellipsoidal shape. And the amplitude of that perturbation, delta R, is proportional to the ratio of the masses of the binary times the radius of the star to its separation from its companion cubed. And so if you now imagine you put this perturbation into your fluid equations and ask what's the fluid's response to this perturbation, well, the fluid equations are inherently nonlinear. And so if you put this perturbation in, you'll get a sort of Taylor series expansion in delta R over R. And so you'll get forces that are linear in delta R over R and forces that are nonlinear in delta R over R, as, for example, delta R over R squared. And so traditionally, studies have ignored the nonlinear terms. They've just kept this linear term, delta R over R, in what you might call linear tidal theory. And there really isn't a great argument for why they did this really it was one of simplicity. It becomes much more complicated to account for these nonlinear terms, and so they just solved the linear problem. But what I'll talk about in this in the talk today is why actually these nonlinear effects can sometimes be very important and actually dominate the dissipation in the system. So, one question you might ask is why adopt this kind of perturbation theory approach? Why not just do a numerical hydro simulation of the entire star? Sort of put a grid across the star and solve the fully nonlinear fluid equations, with some sort of finite differencing or pseudospectral technique. And the problem with that approach is that, as I'll describe, the tide can excite really short wavelength waves in the star, and those waves can have hundreds or thousands of nodes through the star, and it's just not tractable with current computations to solve the fluid dynamics on such short wavelengths over the relatively long timescales that you need to simulate to account for these tidal effects. So really the perturbation theory approach is the only way we can go about addressing some of the questions that we're interested in with respect to tides. Okay, so what are some of the constraints we have on tidal dissipation? So some of the best constraints come from observations of solar binaries. So these are two sun-like stars orbiting each other with sometimes very short period orbits. And so what astronomers have done is they've looked at clusters of stars and tried to find all the solar binaries in those clusters. So for example, here's an optical photograph of the open cluster M35. And here in this plot is the eccentricity versus period of all the solar binaries in that cluster in M35. And so what you notice is that the shortest period solar binaries have essentially circular orbits. Their eccentricity is consistent with 0, while the longer period solar binaries have finite eccentricity. And the interpretation of this is that at short periods, the tides are strong, and so the orbits have been circularized by the tidal effects, whereas at long periods, the tides are weak, and there hasn't been enough time yet since the stars formed to circularize the orbits, and you're basically seeing the eccentricity of formation. And the reason why it's nice to do this for clusters is that stars all formed at essentially the same time, and so you sort of have a stopwatch, and so you can directly see the time scale of the tides by looking at plots like this. And so for this particular cluster, we say that it's has a circularization period of about 10 days. It's been the orbits out to 10 days have been circularized by the tides. And so now you can sort of do the same exercise for different clusters. And so this plot here is showing circularization period versus age for different clusters. So here's this cluster M35 I just showed, which has a circularization period of about 10 days and an age of about 0.1 gigayears. And so there's older clusters that they've done this for, and what they find is that the older clusters have longer circularization periods, and that kind of makes sense. They've had more time to circularize the longer period orbits. And so you can now use this data to try to measure the efficiency of tidal dissipation. And a good way of quantifying the efficiency of tidal dissipation is to talk about the tidal quality factor of the star, the Q of the star. So that's very much like the Q of a bell. So if you strike a bell with a hammer, you can ask how many oscillations does it go through before it undergoes one e-folding of damping. And so the larger Q is, the less dissipative the system is. And so if you try to fit this data here, you see that you need Qs of about 10 to the 5, 10 to the 6 to explain the solar binary circularization periods. And if you then ask, well, what does linear theory predict? And you find that according to linear theory, Q should be about 10 to the 9. So what this is telling you is that linear theory is underestimating the efficiency of tidal dissipation by factors of 1,000. So basically, it's just doing a really bad job at explaining the data. And so there must be some other mechanism, some other source of dissipation in the system that linear theory is not accounting for.
So I'm going to interrupt you very quickly for our first question.
Sure.
Someone asks, in a cluster, how do you distinguish between a binary or multiple system? Don't stars affect each other as they are all gravitationally bound in a cluster?
Yeah, so that's a good question. So that's right. They're bound, especially if you have not an open cluster, but a globular cluster where they're all gravitationally bound. But the typical velocities in these clusters is much smaller than the radial velocities of these binary stars. So these binary stars are really whipping around each other, especially the short period ones. Whereas the overall radial velocity motion of the cluster is much slower. So if you see these really high radial velocities, those two objects must be, or that object is orbiting another object. And the other thing is that in these binaries you can measure the radial velocity as a function of time and see that it has a sort of sinusoidal behavior. Which is because they're orbiting each other, so the radial velocity goes up and down as they orbit. And so both of those things tell you that you have a binary, not just an isolated star moving around in your cluster.
Thank you. And I want to remind everybody that if you do have a question, click on the question button on the right side of your screen there, and feel free to ask one. Thank you.
Thanks. Okay, so this realization that the linear theory is not explaining the solar binary data, and also calculations that we did that show that in a variety of close binaries, not just solar binaries, hot Jupiters, white dwarf binaries, neutron star binaries, in a variety of binaries, the tides are so strong that there's no reason to expect linear theory to be valid. So those effects convinced us to sort of bite the bullet and account for these nonlinear effects. And so one of the key questions we're interested in is, when do these nonlinear effects become important? And when they are important, how do they impact the system? And so in sort of these early papers, we developed some of the formalism and computational techniques to study nonlinear effects in binary systems. And then over the last several years, with various collaborators, including the ones pictured here, we have been applying these tools and techniques to a variety of binary systems, including these ones we're listing here. Right. I'm sorry, my dog is barking. And so, one of the key things that you find when you study tides in binaries is that the tide excites modes of oscillation in the star, waves inside of the star. And a particularly important class of waves that are excited are internal gravity waves. So we've all seen surface gravity waves when we throw a rock in a pond. Stars can support the same kind of waves internal to them. We call them G modes because their restoring force is gravity or buoyancy. And these modes are the ones that are most likely to be excited because they have periods that are of order the orbital period that can occur in these short period binaries. And so in linear theory, you have waves that are excited in the star, but they don't interact with each other. They pass right through each other. They obey the superposition principle. But when you start accounting for nonlinear effects, for example, delta R over R squared effects, you can have wave-wave interactions. And so a particularly important class of wave-wave interaction is the parametric instability, where you have a wave that's directly excited by the tide, what I'll call a parent wave, and if its amplitude is large enough, it can excite daughter waves of half of its frequency. And whether that instability occurs or not depends on the amplitude of the parent wave, whether how close to half the frequency the daughter waves are, the strength of this coupling coefficient, the vertex in this Feynman-like diagram, the damping rate of the modes. But once you have all those things calculated, you can assess whether a system is unstable to this instability. And if it is, you have a new source of dissipation in your system that wasn't there in your linear theory. And in particular, these daughter waves can have very short wavelengths and very high dissipation rates. And so you could dissipate the tidal energy much more efficiently through these interactions than you can according to linear theory. So this is a potential way in which you can increase the star's viscosity, decrease the Q, which is exactly what the solar binary observations are suggesting is going on. Okay, so in a moment I'll show some work we've been doing where we calculate these waves that get excited through nonlinear interactions, and I'll show that there's in these systems can be tens of thousands of modes excited through these interactions. But let me start with just a sort of simplified toy problem where you just have three waves interacting. And actually, before I even show three waves, let me just show what would happen if you set this coupling coefficient to 0 and just had a single parent wave. So in that case, you have the equation describing the parent amplitude is the equation of a driven damped harmonic oscillator. Right, so here, A is the amplitude of the parent wave, gamma is its linear damping rate, omega 1 is its eigenfrequency, and then you have this harmonic forcing due to the tide, where omega is the tidal forcing frequency, which if it's a resonant driving would be close to omega 1. And so let's look at this plot of the parent energy versus time. And so if you start the parent at some small energy and then turn on the tide, it'll start ramping up, and eventually it'll reach some linear equilibrium. And if I extended this plot to the right, it would reach some steady state, some linear energy that it would just sort of asymptote to. But now let me turn on three-wave interactions. So now you get additional terms in this amplitude equation involving the coupling of mode 1 to modes 2 and 3. And what happens is the parent reaches some critical energy shown by this horizontal dashed line here. And when it does, it suddenly becomes unstable to this three-wave interaction and starts resonantly exciting these daughter waves. And those grow exponentially and reach large energies. And then they undergo some sort of complicated limit cycle interaction with the parent. But what you notice is that the parent doesn't reach the linear energy, and the daughters reach an energy that in linear theory the daughters would have essentially zero energy, whereas when you account for these nonlinear effects, they have large energy. And so this is a very different solution than the linear one. And so as a result, the dissipation this system would exhibit would be very different from the linear one. Okay, and so then you can ask in the parameter space of a binary, when is a system unstable to these three-wave interactions? When is the linear energy going to be greater than that critical energy? And so this sort of jagged line here is showing the threshold for this instability to take place. And so anything above that line is going to be unstable to these three-wave interactions. And so as a reference point, I put a hot Jupiter. So a hot Jupiter has a mass of about 10 to the minus 3 of the mass of our sun and a period of 2 or 3 days. And so, so as you can see, it's well into this unstable region, well above this jagged line. If you ask, what about solar binaries? Well, those have a mass ratio of about 1. So they're way off this diagram, and they would be unstable to these three-wave interactions out to tens of days. And so what this plot is telling us is that in almost all binaries in which tides are important, the linear approximation fails. It's just not an appropriate description of the tidal dynamics. And really, you have to account for these nonlinear effects. And so this is true of not just solar binaries and hot Jupiters, but white dwarf binaries and neutron star binaries as well. So this is something that we recognized fairly early on in our studies. And the question then is, what are the implications? And so, what I'd like to do now is describe in detail, one of the systems that we studied, the hot Jupiters and their orbital decay. And so again, these systems are well above the unstable threshold. And so what you find when you calculate the three-way interactions is that the daughter waves, that there's hundreds, actually thousands of daughter waves that get excited by the parent because it's so far above threshold. And those daughter waves reach large energies and excite granddaughter waves. And those granddaughters reach large energies and excite great-granddaughters. And you sort of get this cascade of waves, of modes excited. And so my former PhD student, Reed Essick, did calculations of all the interactions of all these waves that are being excited in sun-like stars. And so his simulations, these are basically networks of coupled nonlinear ODEs. And so he had sort of tens of thousands of interacting G modes in his calculations. And here's just one example of one of his simulations. So it's showing mode energy versus time. The different colors are different modes. And we're actually only showing one out of every 100 modes in the network. Otherwise, it would just be a total blur. And so one of the things you can see right away is that it's kind of, the energy fluctuates in kind of a chaotic, random way. And at one moment, some mode has large energy, and the next moment, a different one does. And sort of there's this sort of complicated dynamics. But if you then ask, what's the total dissipation in the system? So you sum up the dissipation from each mode in your network and get a total dissipation. And so that's what's shown on the plot on the right. And so after sort of an initial burn-in period, when you let these simulations run for long enough, you find that the dissipation reaches a steady value. So basically, the system has reached a nonlinear equilibrium. We say that the system has saturated. And you can then use these calculations to determine what's the dissipation in your star, what's the tidal dissipation due to these nonlinear effects. And so, Reed did just that calculation for, as a function of planet mass and planet period, and you can turn those calculations into a estimate of the Q of the star. And so what he found is that Q is around 3 by 10 to the 5 for a Jupiter mass planet in a one-day orbit. And there's a fairly steep period dependence as well. And so if you express this Q as a orbital decay timescale, so remember these planets, their orbits are decaying due to the torque they exert on the star. And so you can ask, given this Q, what's the timescale for these orbits to decay? And what you find is that they have decay timescales of less than 1 billion years for orbital periods less than 2 days. So less than, timescales less than the main sequence life of the star. Whereas if you did the same sort of calculation in linear theory, ignoring these nonlinear interactions, you would find Qs of 10 to the 9, 10 to the 10, orders of magnitude larger than we were finding with the nonlinear effects. And in linear theory, the system would basically sit there for eternity. For I think it was like 10 to the 12 years. So the star would evolve off the main sequence well before the planet moved at all. So really a very different result when you account for nonlinear effects.
So we have a couple of questions real quick. If I can interrupt, I'm so sorry. The first question is, are some of these waves quantum mechanically coherent as they would be in a nucleus, or should they all be considered as waves in a classical fluid?
So they're waves in a classical fluid. They're standing waves. They're modes of oscillation. But their interaction is not sort of a quantum mechanical kind of interaction, right? It's just a fluid dynamics interaction. Basically, when their amplitudes are large enough, you have to account for these nonlinear terms that introduce these interactions, which is I think different than what you would where the coherence comes from in quantum mechanics.
And then the other question is, someone was asking for clarification concerning the difference between the hot Jupiter type planets that you're studying and the Jupiter that we're more familiar with down the road in the solar system.
Oh, right. Yeah, I should have said that to begin with, right? So the reason they're called hot Jupiters is because they're so close to their host star that they are strongly irradiated by the host star, and so they're hotter than our Jupiter. So our Jupiter has an orbital period of around 11 years, but otherwise they're pretty similar. Similar mass, similar radius. They tend to be a little bit puffed up compared to our Jupiter, but otherwise they're fairly similar. And there's questions about how they got there in the first place while our Jupiter is so far out, and that's sort of another story that actually we're thinking about as well. And their tides are important, probably too, for explaining how you get a hot Jupiter in the first place. But in terms of the objects themselves, they're fairly similar.
Great, thanks.
Okay. Right. So these calculations that Reed and I did a few years ago assumed that the star was a solar type star, but we know of many hot Jupiters that are orbiting non-solar type stars that are more massive or less massive than our sun, more evolved than our sun, younger than our sun. And so it would be very interesting to know what's the impact of tides and nonlinear effects in these other types of stars. If we really want to understand these hot Jupiters, how they got there in the first place and how they're going to evolve in time, we really need to understand their interaction for the range of systems, the range of stellar types that we see. And so this is, one of the problems I'm hoping to work on here with a student. So this is, an opportunity for a student to get involved. So, an important question to ask is, are there observational indications of orbital decay of hot Jupiters? And so there is some statistical evidence. So if you look at the number distribution of hot Jupiters, there's fewer very short period hot Jupiters than you might expect. So there's indications of sort of a clearing out of the shortest period planets. But there's only about a dozen or so really short period hot Jupiters where the tidal effects are really fast. And so the statistics aren't great. There's enough uncertainty to not really be able to say for sure whether Q is indeed as small as 3 by 10 to the 5. But the hope, the expectation is that over the next few years with missions like the TESS space mission, we're going to be finding many more hot Jupiters, and that should give us better statistics to make these kind of measurements and look for these tidal effects. But there is this really interesting hot Jupiter system, WASP-12b, where we think there's direct evidence of orbital decay. So this is a hot Jupiter that was discovered a little more than 10 years ago. It has an orbital period of about 1 day, and that makes it one of the shortest period hot Jupiters that we know about. The host star is a little bit more massive than our sun and about 3 billion years old. And so there's been a couple of groups that have been following the system and doing what are called transit timing observations. So basically, they know where the planet was in 2009, and based on the measurement of the period, they know where it should be today, where in its orbital phase it should be today. And what they find is that it's a little bit further along in its orbit than you would expect if the period were perfectly constant. So they're finding that the period is decreasing at a rate of about 29 milliseconds per year. And so if you turn that into P over P dot, you get a time scale of about 3 million years. So the question is, are we seeing orbital decay? Is this period decreasing because the orbit is decaying? If so, then it would be the first direct evidence of orbital decay, and it would also be incredibly fast. Right? So the time scale here is 3 million years, and yet the star is 3 billion years old. So that sort of may seem like a paradox, and in a moment I'll try to explain what we think is going on. Okay, so this system seemed really interesting to us, and we wanted to see if we could explain these observations, this negative P dot, with a tidal dissipation model. And so if we want to do a calculation of tides, we need to know the structure of the star. And so, because the tides are sensitive to the star's internal structure. And so for measurements of the star's temperature and mean density, we think that the star is either a subgiant, with a mass of about 1.2 solar masses, or a main sequence star with a mass of about 1.35 solar masses. So a subgiant is a star that's consumed its hydrogen in its core and has begun to evolve off the main sequence. And so here's a sort of cartoon picture of what a subgiant looks like. So it has a outer convective envelope and a fully radiative interior. And when you do the calculation of tides, you find that the planet excites a tide at the radiative convective interface, and that tide propagates inwards. And as it propagates inwards, this wave that's excited, this internal gravity wave that's excited, steepens. The amplitude grows and grows, and that's basically just the consequence of geometric focusing. You're trying to put the same amount of wave flux in a smaller and smaller volume, and so the way a wave will do that is its amplitude grows. And so what you find when you do this calculation is that the amplitude becomes larger than the wavelength when the wave approaches the center of the star. Delta R becomes larger than lambda. And so that's the condition for wave breaking. So we've all seen waves break when we go to the beach. These ocean waves travel, in some cases, thousands of kilometers, and then crash at the beach and deposit all their energy right there. And so the same thing is going on with this a wave excited in the star. It's traveling through the entire star and then depositing all of its energy and angular momentum right at the center. And so this is the condition for sort of maximally efficient dissipation. So you can turn that calculation into a orbital decay timescale, a P over P dot. And when we did that, we found a timescale that agrees very well with the measured value of 3 million years. What's more, this scenario can explain how the star and planet can be 3 billion years old, and yet the system is decaying on a 3 million year timescale. So the dissipation only became efficient when the star became a subgiant. You can show that when the star is on the main sequence, its core is convective, and the wave that's excited in the outer part of the star never becomes strongly nonlinear because it reflects off of the convective core before it ever steepens enough. So it's only when the star became a subgiant, which might have only happened a few million years ago, that the dissipation really turned on. So that can explain these sort of seemingly discrepant timescales. There's still the question of, what are the chances of finding such a system? It only spends 0.1% of its life in this phase, but given that there's of order 100 hot Jupiters known, there's kind of a tens of percent chance of finding at least one such system. So maybe it's not so surprising. So I think the story really sort of hangs together nicely. The one sort of remaining loose thread is this question of whether this star is really a subgiant or is it a main sequence star? And really to answer that definitively, we need more precise measurements of the stellar parameters. And so maybe in the coming years, as Gaia's distance measurements become more accurate, and maybe with astroseismic measurements, we'll be able to say for sure whether the star is a subgiant or main sequence. But we think we have a good explanation for what's going on in the system. Okay, so I'd like to switch gears a little bit now and talk about waves excited in isolated stars that are not in a binary. And these waves are excited by internal motions within the star. So in the 1960s, solar astronomers noticed that the surface of the sun is awash in sound waves, what we call P modes, that are excited by the turbulent motions in the sun's outer convective envelope. And so I'll play a movie here of a small patch of the sun, an observation of a small patch of the sun. And these fluctuations you see here are sound waves in the sun. These sound waves have periods of about 5 minutes. And so this movie has been sped up by a lot, so you can actually see the fluctuations. But what's neat is that, while we're seeing the surface manifestation of these waves, they actually propagate through the entire star. And so this is sort of illustrated here. So just like seismologists on Earth use earthquakes to learn about the internal properties of the Earth, helioseismologists use the waves they see in the surface of the sun to learn about the internal properties of the sun. And the way they do this is you can take a power spectrum of these oscillations, basically take a Fourier transform of these oscillations and ask how much power there is as a function of frequency. And what you find is that there's discrete modes, discrete frequencies where there's a lot of power. And these are the individual modes of the sun being excited. And by studying which modes are excited and their frequency spacing and the overall shape of this envelope, you can say very detailed information about the internal properties of the sun. Things like its rotation profile, its sound speed profile, its composition. So we're basically seeing inside the star with these sound waves. And so for 50 years, the sun was really the only star where you could really do this in. But about a decade ago, two space telescopes, especially Socorro and Kepler, especially the Kepler Space Telescope, revolutionized the field. So these telescopes had really good photometric precision. They could see fluctuations in luminosity from a star of just a few parts per million. And that was enough to be able to see these sort of waves rippling on the surface of these stars, basically the flickering of the stars due to these waves in the photosphere. And they did this for a whole type of stars, including tens of thousands of red giants. So red giants are stars that are even more evolved off the main sequence than subgiants. They're no longer burning hydrogen in the core. They have maybe a hydrogen shell burning in the outer parts of their core. But then they've puffed up enormously by factors of 10 or even 100 compared to their main sequence selves. And so these observations, just like with the sun, allowed astroseismologists to calculate the power spectra of the star. And here's just one example of the power spectrum from a red giant. As you see, in black, the radial modes, in red, dipole modes, and so on. So you can look at this power spectrum, and from analyzing it, the frequency spacing and the relative amplitudes, again, just like with the sun, infer really detailed information about the internal properties of these stars, their evolutionary state, their rotation profile. They actually provide a direct way of measuring the mass and radius of the star and age, which is important not only just for stellar physics, but galactic physics, because now we have a way of measuring the age and mass and radius of stars across our galaxy. So it's really just revolutionized this field and impacted a really wide variety of areas of astrophysics. And so one of the neat things that Kepler noticed is that the more evolved a red giant is, the larger the amplitudes of the oscillations. And so this is illustrated this plot here. The more evolved, the larger the red giant, the larger the amplitude of the fluctuations. So this plot at the bottom shows this more quantitatively. So oscillation amplitude in parts per million, delta L over L in parts per million, as a function of the luminosity to mass ratio of the star. And so the sun has, fluctuations of about 1 or 2 parts per million, whereas these red giants have fluctuations that are tens to hundreds of parts per million. And so that means their mode energies are factors of 100 or 1,000 larger than the sun's. And so whereas the sun is kind of has moderately nonlinear effects going on, these red giants, because their energies, the mode energies, are so much larger, are that much more likely to have strong nonlinear effects. And so this result motivated us to apply some of the same techniques we are using to study nonlinear tides for these red giants, these astroseismically observed red giants. And so we're in the process of doing some similar calculations that we did in the context of the tides. In black here, so I'm showing mode energy versus time, and in black here is a parent mode that's being directly excited by the turbulent motions in the convective envelope of a star. And what you find is that its energy is so large that it excites daughter modes shown in red. And those daughter modes reach large energies and excite granddaughter modes shown in blue. And so again, you have this kind of cascade of modes being excited. And one of the questions we're interested in is, how does that impact observables? For example, the amplitude of the modes that are being excited. And so here's just one illustration of the kind of calculations we're doing, where if you now ask what is the energy of the parent mode, if you turn off mode coupling, it's a factor of 1.5 to 2 times larger than with mode coupling. And there are some indications in the data of modes of stars in some of these red giant modes of some of these red giants with suppressed amplitudes. And so we think that that might be due to nonlinear effects. One of the other explanations is magnetic fields, but we think that there might be a purely hydrodynamic explanation for some of these observations. And there's a host of other sort of interesting observables that suggest that maybe nonlinear effects are playing an important role in these systems. And so again, I'm hoping to work with students on problems related to these astroseismic measurements. Okay, so for the last few slides, I'd like to go back to binary systems and talk about a very different phenomenon than waves that I described earlier. So I'd like to talk about what are called X-ray bursts. So these are binaries in which you have a neutron star accreting matter from a companion due to their tidal interaction. Basically, the tides are from the star are pulling off matter from its companion, and typically the companion is a sun-like star. In some cases, we think it's a white dwarf, but this matter forms an accretion disk around the neutron star, and eventually accretes onto the surface of the neutron star. And we know of about 100 of these what are called low mass X-ray binaries in our galaxy. They're X-ray binaries because the accretion disk is so hot that it's emitting primarily in the X-rays. And so what happens during this accretion process is you accumulate, or the neutron star accumulates, a critical layer of fuel. So you're accreting mostly hydrogen and helium, and a critical layer of fuel accumulates and eventually undergoes an unstable thermonuclear reaction. Basically, the helium and hydrogen ignite, and whereas it takes maybe hours to days to accumulate, it all burns in a matter of seconds, and you get a bright flash of X-rays, this X-ray burst. And so they're seen with a variety of X-ray telescopes, for example, XTE, Chandra, XMM, and most recently with the NICER telescope on the International Space Station. And so here's a light curve of the NICER telescope. So you have count rate as a function of time. And so you have a fast rise in this event. So this is a burst from a source called 1820 minus 30. And so you have a fast rise, which is the burning phase of the event. And then you have this kind of long tail, which is the cooling phase, when you burnt all your fuel and now you're just cooling off. And so in this case, the burst lasts of order 10 seconds, but depending on the ignition depth of the burst, it can last minutes to hours in some cases. If there's more fuel that's accumulated before ignition, the bursts tend to last for much longer. And so, one of the things that makes these X-ray bursts really interesting is they provide some of the best constraints we have on the radius of a neutron star from these events. So as I sort of alluded to in the beginning of the talk, these neutron stars are mysterious objects. We don't really understand the equation of state in their cores. And if we can measure the mass and radius of a neutron star, we can place constraints on this high-density equation of state. And so I won't go into detail exactly how you can do this with X-ray bursts, but there's a number of groups doing these kind of, looking at these light curves and analyzing the spectra from bursts and making measurements of the mass and radius of neutron stars. So that's illustrated in this plot on the bottom here. And so, one of the issues with this measurement, with these measurements, is there's a number of assumptions. They have to go from the observables to a radius and mass measurement. And so there's been concern over the years about systematic errors in that process? Do we really understand all the physics going on in these systems to go from an observable, like the burst spectrum and light curve, to radius measurement? And so really what this is saying is that we need better models of these events, of X-ray bursts. And so this is something that I've worked on for a fair bit of time, actually since I was in graduate school. And so I just wanted to go a little bit into some of the physics of an X-ray burst. So what happens is you accumulate this layer of hydrogen and helium, and in a typical event, you might accumulate about 10 meters of material. And below here, this this burning shell is at the neutron star surface. Below here, you have about 10 kilometers of neutron star. And so you accumulate this 10 meters, and suddenly the temperature and density become high enough that you ignite the helium at the base and very quickly burn that fuel. And the luminosity from that burning is so high that it drives convection in the atmosphere of the secreted layer. And that convection mixes the ashes of burning from the base upwards. And so you get heavy elements, silicon, sulfur, up to things like iron and nickel, mixed within these convective regions of the burst of the atmosphere. And so last year, my former PhD student Hong Yu and I carried out the first simulations of winds from X-ray bursts. So some of these bursts have such high luminosities that they drive radiation-driven winds. Not all of them do, but some fair number of them do. And what we found in these simulations is that the base of the wind, the location from which from where the wind is launched, is located within the convective layers of the atmosphere. And so what that implies is that this wind will be infused with ashes of burning, these heavy elements that were just synthesized during the burst. And so that got us really excited, because it meant that maybe observations with high enough spectral resolution could see these heavy elements, basically the absorption edges from these heavy elements, and use those observations to say something about the burst physics as well. If you can measure a gravitational redshift from the absorption edges, you can infer, you can use that gravitational redshift to say something about the mass and radius of the neutron star. So a few months after we put this paper out, the NICER telescope reported the first strong detection of absorption lines in X-ray bursts. So previous X-ray telescopes weren't sensitive enough at these lower X-ray energies below about 0.2 keV, and didn't have the spectral resolution to see these absorption lines. They basically were just able to see the black body temperatures, but they didn't have the resolution to see absorption lines. But NICER made that first sort of convincing detection of absorption lines, consistent with some of the results that we were finding in our calculations. And so they saw a helium-like sulfur line with indications of wind-induced blue shift and a gravitational redshift. And so we're very excited about this, and we have I work with some observers in the Netherlands and in Australia, where we have a NICER proposal to look at what we think is a really interesting source for 160 kiloseconds, to look for more of these absorption lines, and potentially maybe with NICER, or maybe if we get Chandra time, to look for a gravitational redshift, which would be a whole other way of constraining the radii of these neutron stars. And so these simulations that we did last year were relatively simplistic. Again, they were the first hydrodynamic simulations, first time-dependent simulation of winds. And so anytime you do something first, there tends to be simplified treatment. And so this is 1D Newtonian. We didn't do particularly sophisticated radiative transfer. And so our plan now, some something that I'm very excited about is to use a code called Athena++, which is an adaptive mesh radiation hydrodynamics code to do more realistic simulations of burst winds. So do it in full GR, multi-dimensional, more sophisticated radiative transfer. And this is in collaboration with Shane Davis at the University of Virginia, who's an expert at Athena++ and who does a lot of simulations of accretion disks around black holes. And so we're planning to put in NSF proposal to study this problem. And so again, this is another, I think, opportunity for students to get involved if you're interested in this kind of problem. So I'll just quickly wrap up. One of the, I think, takeaway points is that this linear approximation that has sort of been the standard in the field for a long time really doesn't seem to be appropriate in tidal systems. So I talked about the impact of nonlinear effects in hot Jupiter systems. I didn't have time in this talk to describe the work we've been doing on neutron stars and white dwarfs, but these nonlinear effects can be important there as well. I talked a bit about nonlinear effects in red giants and how those can impact observables like the mode amplitude and line width and frequencies. I talked a little bit about X-ray bursts and how we're hoping to do more realistic simulations in the future. And one of the things I hope I conveyed is that there's really exciting set of observations that exist today, and that will more observations that will come in future years with these various observatories. And so astrophysics is a very data-driven field. And so, these new observations, get theorists excited because they sort of provide an opportunity to really test our understanding of these systems. And so, again, there's, I think, a variety of opportunities for students, both graduate students and undergraduate students, if you're out there in the audience, to get involved. And so if any of this sounded interesting to you, I'd be very happy to meet with you and talk more about it, and maybe we can come up with a problem to work on together. So with that, thank you very much for your attention.
Thank you very much. I greatly appreciate it. What is the best way for interested students and researchers to get a hold of you? What's your email?
So my email is pretty simple, nevin@uta.edu.
nevin@uta.edu. I'm going to go ahead and share that in the Q&A. And of course, we have some questions. Our own Suman Satyal asked, would binary tidal forces affect the inner stability limit of circumbinary planets? Maybe we can apply your theory to known 10 or 12 Kepler circumbinary systems and figure out the inner boundary between binary and planet.
In principle, yes. So I haven't, when you start talking about three-body systems, things quickly become much more complicated, and so even doing the point mass studies is difficult. But yes, in principle, tidal effects, if they induce orbital decay, can also change the stability limits. It's not a problem I've been courageous enough yet to work on, but it does. I think it is an interesting question.
And another question referring to a few slides back was, how far out would these heavy elements be spread out based on hydro models from the surface of neutron stars driven by these winds?
Yeah, so these winds, they're often referred to as radius expansion bursts, or photospheric radius expansion bursts. And so the photosphere actually expands out from 10 kilometers to where they're on when it's on the surface of the neutron star, out to hundreds or even thousands of kilometers. So basically, these ashes are ejected from the system. They're just unbound from the neutron star. But what happens is then the burst sort of cools down, the atmosphere cools down, and the wind turns off, and these ashes settle back down, or those that weren't ejected completely settle back down onto the neutron star surface. And so it's actually those ashes that we think would provide if we can see them, their absorption edges or their lines, provide a potential way of measuring the gravitational redshift of the neutron star. But yeah, I mean, in the simulations that Hong did, he's following this material out to hundreds of kilometers.
We have one more question. Do pulsars add advantages or challenges to the modeling and observability?
Yeah, so I would say challenges because now you have magnetic fields involved. The fortunate thing is that for most of these low mass X-ray binaries that are showing X-ray bursts, the magnetic fields are actually quite small, less than about 10 to the 8 Gauss, whereas a typical pulsar might have a magnetic field of 10 to the 12 Gauss. And the reason we think they're small is because basically they've gotten buried by all the material that has been accreting onto the neutron star for millions of years. And so basically, to a good approximation, the magnetic fields don't impact the X-ray burst itself. A more significant impact comes from the rotation of some of these systems. So some of these systems can be spinning with frequencies of hundreds of hertz, and there the fluid dynamics becomes more complicated. But there are also systems that are spinning much more slowly. So spin is important, but probably not so much magnetic fields for these events.
Okay, well, I think at this point we are out of questions, and I want to go ahead and thank our speaker one more time and invite everybody to join us again next week. Thank you so much.
Thank you. Thanks, everyone.